Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In the previous video 45, we explored matrix multiplication using a triple-nested loop with OpenMP for parallel computing, utilizing the Intel Fortran compiler loaded through the NRIS module system. In this video, we will use the MKL routine for matrix multiplication with OpenMP, once again using the Intel Fortran compiler loaded through the NRIS module system. We will also do a scaling analysis. This analysis involves measuring computation times while varying the number of threads, starting with a single thread and scaling up to 256 threads. Scaling analysis is a technique in parallel computing used to assess how effectively a system performs as more processing units are added. It helps identify whether increasing computational resources leads to performance improvements and to what extent. This process is vital for optimizing parallel systems and ensuring resources are utilized efficiently. In video 45, I reviewed how to use the NRIS module system, and in this video, I will once again use the CPU module system. I am already logged in to Olivia and currently inside the MXM, OpenMP, and NRIS Intel folder. I will begin by listing the contents of this folder. Let's start by examining the Fortran program that performs matrix multiplication using the MKL routine. I will start by testing the program with a matrix dimension of 32, 7, 68. Otherwise, the program is like the one used in video 43 and 44. I am using allocatable matrices in this program as explained in video 43. After reviewing the code, I exit the Emacs editor and return to the terminal. We will now examine the job script used to execute the Fortran program. The job script is very similar to the one used in video 45 with the NRIS module system, but this time I am using the MKL routine. The script compiles the Fortran program using the Intel Fortran compiler with same options as in video 45, but the mat-mul option has been replaced with options for using the MKL routine. I am not using the Xhost option as it causes a segmentation fault, as observed in video 34 when using the MKL routine on Betsy. After exiting the job script and returning to the terminal, I can clear the terminal. I can execute the Fortran program by submitting the job script to the Slurm queue system. We can see that the job is assigned the number 4030. When I check the Slurm queue with the Me option, we can see that the job has already finished. Using the More command, I will open the Slurm job output file. The matrix multiplication using MKL and the Intel Fortran compiler was completed in about 8.5 seconds on 256 cores. The job output file shows that the CPU efficiency was about 74% and the memory usage was about 25 gigabytes. In videos 43 and 44, we observed that the Fortran program using the MKL routine included in the Cray scientific library had a memory usage of approximately 44 gigabytes. The increase in memory usage when using MKL from the Cray scientific library is due to internal optimizations and temporary buffers utilized by the library to achieve high performance. Here, we can see that the MKL library included in the NRIS module system uses no more than 25 gigabytes of memory. This indicates that the MKL library in the NRIS module system is not able to perform the same level of optimization as the MKL library accessed through the Cray module system. The computation time using the Cray module system was approximately 5 seconds, as shown in videos 43 and 44. Whereas with the NRIS module system, the computation time is about 8.5 seconds, as seen in this job output file. This means the MKL routine with the Cray module system is approximately 1.7 times faster than the MKL routine with the NRIS module system. I will now perform a scaling analysis of MKL with the Intel Fortran compiler on Olivia, but first I will clear the terminal. I will first list the contents of my folder. I will use the same method as in videos 44 and 45. This approach involves using a Python script named Setup Testing OpenMP for the scaling analysis, so let's take a look at it. The script uses the OS module to execute Linux commands and was previously reviewed in video 44. In this script, a Python for loop is used to run the sbatch command multiple times. Each command is printed to the terminal before being executed through the OS module. Let's exit the Emacs editor and return to the terminal to examine another file used in the scaling analysis. This script is named Testing OpenMP, as in our previous videos. This script will not compile the Fortran program, but use the executable we generated in this video, using the MXM OpenMP MKL job script. We can take a look on this testing script. The script is very similar to the job script I have used in this video. The first difference is that it requests one node, but the number of tasks and CPUs per task, or threads, is specified differently and not directly in the script. The second difference is that the job requests 753 gigabytes of memory. The reason for this is explained in video 44, and this ensures that each scaling test job is executed exclusively on a single compute node. The third difference is that the script does not compile the Fortran program, but instead uses the compiled executable MXM I have produced in this video. The program is executed 3 times, and these wall times can be used to calculate an average for the matrix multiplication. After returning to the terminal, I can clear the terminal. I have the Python module in my home environment, as explained in video 44, and will begin the scaling analysis by executing the Python script. The terminal displays the sbatch commands executed by the script. We can see that the number of tasks and CPUs per task is now specified on the command line when submitting the testing script. Applying the slurm q command with the me option, I can confirm that all my jobs have started on different nodes. Before checking the results, I will clear the terminal. I use the ls command to list the folder contents. Let's examine the last job output file using the more command. From this file, we can see that using 256 threads results in a wall time of approximately 8 seconds. We observe that the memory usage is about 25 gigabytes. I use the data from these scaling tests to create figures showing the wall time and CPU time, similar to what was done in videos 12 through 16. The first figure displays the wall time and CPU time, using a logarithmic scale on the time axis. The second figure presents the same data but uses a logarithmic scale on both axes. Let me first enter the number of threads or cores used in the scaling analysis. I can add the mean wall times to the figure. I will enter the CPU times, calculated by multiplying the wall times by the number of cores used. Finally, I include the speedup factors between tests. The CPU time was plotted to illustrate that, in an ideal scenario with perfect scaling, the curve would form a straight line, indicating a consistent speedup factor of 2 across all tests. We observe a near-perfect speedup up to 16 cores. The scaling analysis shows that a computation taking about 1,204 seconds on a single core is reduced to approximately 79.4 seconds on 16 cores, achieving a speedup of around 15.2. In an ideal scenario with perfect speedup, this would have been 16. The speedup decreases when scaling from 16 to 64 cores. The scaling analysis indicates that a computation taking approximately 79.4 seconds on 16 cores is reduced to about 25 seconds on 64 cores, achieving a speedup of roughly 3.2. In an ideal case with perfect speedup, this would have been 4. The speedup remains at the same level when scaling to 256 cores. The scaling analysis shows that a computation taking 25 seconds on 64 cores is reduced to about 7.92 seconds on 256 cores, achieving a speedup of 3.2 instead of the ideal speedup of 4. The scaling analysis reveals that a computation requiring 1,204 seconds on a single core is reduced to 7.92 seconds on 256 cores, achieving a speedup of about 152, which falls short of the perfect speedup of 256. A perfect speedup is unattainable because, as explained in video 11, there will always be sections of a program that cannot execute in parallel. These sequential sections increasingly limit the speed-up factor as the number of cores used for parallel computing grows. As observed in these scaling analyses, there is near-perfect speedup up to 16 cores, but this diminishes when using more than 16 cores. We have now conducted a scaling test using Intel MKL loaded through the NRIS module system. In the next video, we will once again use the Intel Fortran compiler, but this time it will be loaded through the Cray module system. I am looking forward to the next video. Wishing you all happy computing in the meantime.